All right, so here we are to talk about active transport and membrane potential, specifically pumps. So the first thing that we need to understand is what a concentration gradient is. And a concentration gradient is any time you have a cell membrane or any kind of membrane really, and on one side you have a high concentration and on the other side you have a low concentration. Okay, so you have high, low. And so that is what a gradient is. It's where you have a different concentration on each side of the membrane. Active transport is the only way that that's going to happen, because naturally what's going to happen is these guys are going to want to come over here where it's less crowded. And so they're going to want to go to, in this case, to the right. But sometimes we don't want that. Sometimes we want them to stay over here so that we can have them do that, this falling down the concentration gradient, when it suits us. So sometimes we want to hold them here so that they can fall down when we need them to. We can then cross back over to that low concentration when we need them to and not when they want to. And so active transport is going to allow us to keep pumping more into that high concentration against what it wants, because again, they want to fall to the low, but we're going to pump and add more and more and more, but it's going to require energy because they don't want to do that. And so pumps are one way that that this happens. So it says, I can describe how pumps function to complete active transport. Well, a pump is just what it sounds like. It's going to pump something across. It's going to take a molecule and it's going to shuttle it or shoot it over into that high concentration. In this example, we're going to have H+ ions, which are hydrogen ions, basically just a proton, and we're going to shuttle them up to the high concentration. And this pump is going to do that. It's called a proton pump because, again, hydrogen ion is really just a proton. So it's going to pump these hydrogens from low concentration to high concentration. And it's going to do that against what it wants. It's going to have to work or use energy in order to accomplish that task. So I can describe how pumps function to complete active transport. They're literally going to move molecules from a low concentration to a high, and they do that through the use of energy. I can give an example of a pump. Here is our sodium potassium ATPase, is what it's called. And it is basically what we used to call the sodium potassium pump. And what it's going to do is, this is a neuron, and this neuron has already fired. It's already gone through its action potential where the sodiums have fallen in, and that's created that action potential that just shoots right down the axon. And what we want to do now is we want to reset that action potential, or reset that neuron back to its resting state. And the way we do that is with the sodium potassium pump. What it's going to do is it is going to pump sodiums Na back out, and in doing so, it is and we'll talk about this in a second, it's an antiport. It has to pump 3 sodiums out, so this is 3 sodiums for every 2 potassiums in. So what it's going to do is it's going to move these potassiums in, it's going to move these sodiums out, and right now that's a high concentration, but as we move more sodiums and more sodiums and more sodiums, you're going to start to get a high concentration of sodium out here, but there may still be some in here that need to go out. And so this pump is going to use ATP, or energy, to pump those NAs in and then pump those potassiums, pump those sodiums or NAs out and pump those potassiums back in. And so that's an example of a pump. I can describe how a membrane potential is an electrochemical gradient. Well, let's look at this up here. So a membrane potential, I skipped one. I can define membrane potential. A membrane potential is basically the potential energy that is stored when we have a high concentration and a low concentration, when we have a gradient. Because what wants to happen is these H's want to fall back through, but we're not letting them. So by stopping that process, we are holding them up here until the time is right for us to have them fall back through another protein, and we can then use that to make some stuff. We'll talk about that in the next unit with photosynthesis and respiration. But because we're holding them up here, there is potential energy because they are like waiting. It's kind of like runners at the running block at the beginning of a race. They're like here on their heels, ready to jump and cross back over this membrane as soon as they can. So they're just kind of like waiting to jump, but they can't. And so that's potential energy. So the membrane potential is simply the fact that we have created potential energy by creating a high concentration of hydrogens and not letting them cross back to the low concentration. So that's potential energy that will be released when we do let them flow down later. So I can describe how a membrane potential is an electrochemical gradient. All right, so let's break those words down. You understand, hopefully, at this point what membrane potential is. Okay, it's just that gradient that we have here that's creating this desire for these guys to come down, but because we won't let them, they're stuck there and they're just, their potential energy waiting to jump. Electrochemical gradient, you know what gradient means. A gradient is anytime you have two different concentrations on either side of a membrane. Electro and chemical are going to talk about what we're looking at. So electro is looking at the charges. So if I counted all these up, I'm 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's my charge out here, and 4 is what I have in here. So when you have cells, you can actually take a little tiny baby voltmeter, and you can stick it inside the cell, and you can stick it in the extracellular space, and you can take a voltage or a measurement of the volts inside and outside, a measurement of that electrical charge. And so when you have ions, when there are different amounts of ions, you're creating an electrical gradient. You're creating a difference in electrical charges on either side of a membrane. Okay, as far as the chemical part of that, because it is an electrochemical gradient, the chemical is simply the fact that we're talking about atoms. We have 15 hydrogens up here, we have 4 hydrogens down here. So the fact that we have a different number of atoms, chemical, is our chemical gradient. So when we talk about an electrochemical gradient, we are talking about when we have ions that are uneven on either side of a membrane. And again, that's going to cause that membrane potential because we have all these guys here that just want to jump down here. Okay, I can explain why active transport is needed to create this membrane potential or electrochemical gradient. The reason is what we really want to do is we want to pump these H's up here. Well, they don't want to go up there. There's already 15. They're like, hey, we got all the space down here. Let's stay here. And the cell says, no, I really need you up here because I'm going to need you later to fall back down and do something for me when you do that. And so it's going to pump all of these H's up here. Well, it's not going to do that passively. The cell is just not going to, or the hydrogens are not going to just flow up there and just out of the goodness of their heart. They're going to have to be forced to go up there because it's already crowded and they don't want that. And so because we're having to force them, we're going to have to use energy. And so that is why we have to use active transport specifically, not passive, to create that membrane potential. All right, the last two things are I can define cotransport and I can define symport and antiport. All right, so let me draw some really basic cell membranes down here with some proteins in them. Okay. All right, so cotransport, there are some proteins, and the sodium potassium ATPase is an example, that have to move 2 molecules together at one time. They can't do just one. So a uniport, which is the opposite of cotransport, can move 1 molecule through. This hydrogen or proton pump up here is a uniport because it's just moving 1 hydrogen through. But like I said, some can't do that. So some do what we call cotransport. If the molecules are moving in the same direction, that is a symport. Okay, so let's say that you need to bring some glucose into the cell, but you have to do water too. That for whatever reason, this protein says you can't bring in glucose without water, but you're moving them both into the cell. That would be a symport. If it's an antiport, anti means opposite or against, and so it's where we have things going in opposite directions. Your sodium-potassium pump is a good example, or sodium-potassium ATPase is a good example of this because the sodiums are going out and the potassiums are coming in, so they're going against each other direction-wise. And so that is an overview of pumps and how they help create membrane potentials and electrochemical gradients. Also examples of cotransport and the difference between symports and antiports. I hope that helps. If you have any more questions, let me know.